Hi. Thank you for coming. This is me, Adel Bibi, and this is a joint work with Hani Itani, supervised by Dr. Ghanem. And I'll be talking about solving large-scale lassos in the Fourier domain. So I'll start off with some of the boring material. So I'll introduce to you the lasso and some important applications of computer vision. So this is the optimization problem that we seek to solve. Essentially, we want to find a vector C that fits the data with an L1 prior that induces sparsity. So we seek to find a sparse solution that best explains the data. The problem in hand is convex, however, it's not smooth. And we will donate the matrix throughout this presentation A, which is often fat, as a dictionary, and the solution C as a sparse code. So as for the applications and where large scales come into play, we'll examine a classical face recognition as an example. So for face recognition, for instance, the dictionary matrix A is composed here of, say, several blocks, T blocks in this particular fashion. Each block represents a concatenation of, say, vectorized image patches of a given person for each block under the different lighting conditions, for instance. So if we have a T number of blocks, we have T number of peoples to recognize among. So given a new test sample B that we require to determine to what person it belongs to, we look at the solution C and we look at where the most non-zero elements are condensed, and that gives us an intuition to what class label does B belong to. So here we can see easily where large scales come into play. So as for the number of columns, the more number of sets or people that we want to distinguish among, the more number of columns we have, and obviously the more diversity within each column, each block or person we have, the more columns we have. As for the number of rows, well, it is vectorized image patches, and that's self-explanatory. So in either ways, the dictionary A is large in at least one of the two dimensions, if not both together. So the applications obviously expand to tracking and subspace clustering, image and painting, and many other more. So in general, the deterministic lasso solvers are either first-order or second-order methods. And in here, I emphasize deterministic solver to highlight that there exists some randomized methods to solve large-scale linear systems. In particular, there has been a direction towards solving the lasso. However, this is not the focus of this work. So first-order deterministic solvers enjoy inexpensive iteration costs with linear rates, often. Proximal point methods and ADMMs are a good example for that. As for second-order methods, we require to compute the Hessian or proxy version of it, so that have it high expensive iteration costs, but enjoying quadratic rates. And primal dual interior point methods are a good example for that. So however, the focus of this talk, as I mentioned, would be on deterministic first-order methods. So if we look at the lasso problem, I would like to apply ADMM directly to it. There are two ways. We either apply ADMM to the lasso, or we apply ADMM to the dual version of the lasso. And we'll donate them as PL ADMM and DL ADMM, respectively. And the bottleneck really here is solving a linear system. In a primal lasso, it's of size n pi n, while in the dual lasso, it's of size of m pi m. Well, given that the matrix A is often fat, has more columns than a number of rows, so it's more attractive to actually go for the dual lasso intuitively. And that is actually has been shown empirically. This is one of the best deterministic first-order solvers to tackle the problem empirically, and it naturally handles linear constraints. However, it still requires solving a linear system which is not trivially parallelized over multiple GPUs and does not do well when it comes to scalability issues. So what we really want here is to have a solver that has a low iteration complexity, enjoys the linear rates, and can be trivially parallelized over multiple GPUs. So what we really need, the question that we asked ourselves is, do we benefit from lifting the problem to a higher dimension and equip that new dimension with some structure that can help us eventually solving the problem? So well, that's exactly what we've done. We generate an even bigger problem than what we started with by looking at each one of these columns and generating the original matrix A and generating a circulant matrix out of it. So if the original matrix A was of size m pi n, then new A tilde is now of size m pi mn. And to make sure both problems are in fact equivalent, extra constraints are added to force that the coefficients of the new sparse code C tilde corresponding to the extra columns we have appended to be exactly 0. Concatenating to the linear constraint DC tilde equals to 0. So I'll keep the intuition behind this lifting problem and how it correlates to some dictionary learning methods, for example, the convolution sparse coding, where this looks very similar to the inference step of the convolution sparse coding. However, the sparse codes are constrained to belong to the set of discrete impulse functions. But we can discuss the details of this offline. So here's the big picture. And on your left is the primal and dual versions of the lasso, where PL ADMM, dual ADMM is applying ADMM to each. On your right is the lifted problem, and right beneath it is the dual version. And FFTLasso is essentially applying ADMM to the dual version of the lifted problem, for similar reasons why DL ADMM is more attractive than the primal ADMM. So all right, so we need to look at the solutions for the update solutions for FFTLasso to see why is it exactly more attractive than dual ADMM. So the dual variable psi update, the updates for psi, for instance, still requires solving linear systems. However, there is structure in A tilde Hermitian, which allows us now to solve the updates completely in the Fourier domain by using the diagonalization of these circulant matrices. And we no longer now need to do any linear system solving nor matrix vector multiplication, and the FFT is the most expensive operation. And in fact, if we look at all the remaining updates, all of them involve only element-wise operations, and again, FTs are the most expensive operations. So lastly, the dual variables here of the dual problem are the primal variables. So C tilde here is in fact the sparse codes that we seek, the lifted sparse codes that we seek, and they are often updated with a standard dual ascent step. We, however, in FFTLasso solve the problem with a Nestrov's-like update to improve the convergence. So Q here is related to the condition number. However, we set it as hyperparameter throughout the experiments. So upon convergence, the final solution C tilde can be obtained simply by downsampling the solution C tilde. So to give you an idea of the overall complexity, FFTLasso's most expensive operation is computing FFTs with mn log m, as compared to at most m cubed for linear system solving. This indicates that FFTLasso is best suited for matrices that satisfy this inequality. This is the case for dictionaries that are large in both dimensions, however, does not have significantly more columns and has rows. So since that I mentioned all the operations are element-wise, I will have to look first at some of the synthetic experiments that we have done. So we compare FFTLasso first on two GPUs, Maxwell and Pascal, against a multi-core CPU version of dual ADMM. So despite that CPU cores are much faster than the GPU cores, sometimes 3 times as fast, and there are many powerful linear system solvers, FFTLasso still outperforms dual ADMM for larger problems, and of course, it's not faster for the smaller problems. And you can notice that there are some dips in the performance. They happen exactly at powers of 2, and we can discuss the details of this offline and how to circumvent these sort of issues. Another experiment is on synthetic data as well, so we compare now both methods on the GPU. So when Q is 1, we are now here performing standard dual ascent step, where Q equals 30 or not 1, this is the Nestrov's update. So notice that actually using the Nestrov's on dual ADMM actually improves the dual ADMM. However, FFTLasso benefits more since it requires more number of iterations overall to converge, since it has a significantly more number of variables. So we also managed to get our hands on the 24 gigs P6000. So we have added another data point to that previous plot, which is for matrices of 16,000 by 16,000. And we noticed that the improvement in speed could go up to 6 to 10 folds. So the question here is, what happens if we started with a dictionary that is so large that we can't even fit it into one single GPU? What can we do there? Well, that's easy, because now we can actually split the dictionary into arbitrary number of vertical splits and throw each split in a different GPU and aggregate the results at each iteration. However, that requires us to have an overhead of m vectors of size m to aggregate at each iteration. So the question is, can we do better than that? And the answer is yes. If we break that dictionary into even and odd indices and recursively apply that, we can actually now tackle the problem where we can relate the FFTs of longer vectors with respect to their smaller components. And thus, we can actually now break the matrix into arbitrary number of pieces and throw each piece on a GPU, either it was a vertical or horizontal split. And now the overhead is also reduced to m over v, where v is the number of splits horizontally. So to remind you, the face recognition, so all the previous ones were synthetic data. So if we look at some face recognition data set, we conducted it on Yale base B data set. So in both experiments here, we have 10,000 images. And on your left, we have a total of 2 to the 12 pixels, vectorized image patches, which is the number of rows. And on the right is 2 to the 13 number of pixels. So for this experiment, we'll compare FFTLasso to the dual ADMM by giving both solvers the same exact amount of time. And we compare the quality of the solution for both methods with a pre-computed solution, high accuracy pre-computed solution. So FFTLasso converges to much better solutions than ADMM for a fixed amount of time. And this also verifies why large scale and going to large scale is really important, because as you can see, going from 2 to the 12 to the 2 to the 13 pixels, we jump from 92 to 97% accuracy in recognition rate. So to sum up, FFTLasso is easily distributed. It's also memory efficient, which is something we can discuss later on. And it can naturally handle, of course, linear constraint without actually added any complexity. For example, what if we want to tackle problems like constrained lassos? And some future direction would be looking at some other non-smooth regularizers, since we're mostly interested in the data fitting term. So we have a code for this, thanks to these folks for helping in several developments. So we have a TensorFlow version of it for a multi-core, multi-GPU version of it, where you can just specify the number of GPUs and we'll distribute it over them. Thank you for your listening, and please come see us at Poster 10.